always love to hear from you. Send us your views, comments, and videos with your name and town to the One Africa TV's WhatsApp on 081 200 6659 or send an SMS to 555. One Africa TV, it just gets better.
Distillation and fractional distillation. People, we use distillation or fractional distillation to separate substances that have, there is video, sound. To separate substances that have different boiling points. Or, if for example, we had a look at an example yesterday of crystallization where we had a mixture of salt, say for argument's sake, dissolved in water. Then you can evaporate off the water and you are left with table salt. But let's say you're not interested in the table salt as such, you want the water. Then you would be able to do a distillation to remove the liquid part from something that is dissolved in it. Okay. Now, distillation simply works on the basis of if you have substances with different boiling points, you can boil off the one substance with the lowest boiling point first, and you can condense it, and you can catch it up, and then you can get the next one with the higher boiling point. Now, this only works very well if the boiling points differ with about 50 degrees Celsius. Okay, so, well, with liquids of which the boiling point differs with about 50 degrees. Okay. Now, we use an apparatus, this thing over here, called a Liebig condenser. Over here, that part there is a Liebig condenser. Now, it's a simple process. You will take your mixture and you will heat it up. You'll have a thermometer so that you will know what temperature this mixture is at, so that you can control the heat of the flame so that only the first substance vaporizes. So the vapor rises up, okay, and it goes down this tube there, okay. But now circulating around this inner tube over here, we have water. The water goes in there, it circulates around the tube over here. All right, remember, this is a flat diagram. It's a three-dimensional structure. It's a tube with a tube in it. And the water circulates around this gray part. No? Okay. So it cools down the vapor and it condenses, and the condensate is caught up in a container. All right. What is important with the Liebig condenser is that you must remember that the cold water goes in at the bottom, and the warmer water will come out at the top, so that we find there's an exchange of heat. As the warm vapor comes down the tube, the cold water is circulated in the opposite direction. And it allows for a longer time of contact with fresh cold water to exchange the heat effectively. So always cold water in on the bottom, the warmer water is circulated out on the top. Note the other apparatus. Here I have a retort stand with a clamp. There's my retort stand. There. There's my clamp. What would the name of this container be? That one would be what type of flask? A round-bottomed flask. No, it's got a round bottom, so that's a round-bottomed flask. Got the Bunsen burner and a thermometer. Now, sometimes we have more than one liquid in a mixture, and their boiling points are slightly closer together. All right? Then we do a process called fractional distillation. And to do fractional distillation, we add a long column on top of the flask over here. Can you see we just had the thermometer in it? By fractional distillation, we extend the neck of the flask with a long column, and usually inside that column, we find something like glass beads. All right, and all that happens is, as the liquids vaporize, they rise up, but as they rise up, they start cooling. All right, but the one with the lowest boiling point will be able to go up the highest before it condenses. So we find that if you maintain the temperature, say there's a liquid that has to vaporize at 40 degrees, you maintain the temperature at 40 degrees, the vapor will rise up. But if there's a liquid, let's say 45 degrees, it's also going to rise up. But somewhere along the line, it's going to condense and drip back into the flask. And only the one that vaporizes at 40 degrees will the vapor be able to enter the tube of the Liebig condenser. The liquid will be condensed and it can be caught up. Now, this is actually a very long process to remove the different fractions from the mixture. In the petrochemical industry, they have a more complicated fractioning column. And seriously. Okay, let's just leave it at that. We have a setup known as a fractioning column. And all that happens is, over here is a container in which the crude oil is pumped into it. It's heated, and everything vaporizes. All right? Then it's allowed to enter this column, this chamber, the fractioning column. And we find substances with the lowest boiling point, in other words, those that would normally be gases at room temperature, for example, the gas that they use for gas stoves, all right, they rise right up to the top of the fractioning column. They don't want to condense because at room temperature, they are still gases, and they are caught up as gas, then refinery bottled gas. We use it for cooking on stoves. I think that's the most common one. The laboratory Bunsen burners work with gas from there. Then we find that the liquids with the next highest boiling points, 40 to 205 degrees, they will condense over here, and they are tapped off over there. Simultaneously, those with a higher boiling point taps off on the next level, and the next level, and the next level, and the next level. So in one go, they can separate out 1, 2, 3, 4, 5, 6, 7, 8 different fractions. All right. This is how they separate the different parts of crude oil. If you think about petrol and diesel, if you had to compare the two, petrol evaporates. Does diesel evaporate? No, not really. Why not? Because petrol has a boiling point between 40 and higher than that, all right? While diesel is over here between 250 and 350. So diesel is stickier, doesn't want to evaporate very easily. The forces holding the particles together are stronger than in petrol. That is why petrol has a lower boiling point. Yeah, that is why you keep your petrol tank sealed shut, because it wants to start vaporizing at those temperatures. All right. I don't think it's exactly 40, but I think it's probably nearby. Petrol is also a mixture. It contains molecules of, I think, approximately 6 carbons to about 12 carbons in the chain. All right. And the 6 carbon one will evaporate easier than the 12 carbon chain. All right. Diesel and these fuels are much longer molecules, much bigger molecules, so they are heavier. It's more difficult to make them evaporate or then cause them to boil. Okay, so the fractioning column, what is very important is the increase in boiling point. Those with the lowest boiling points, in other words, those that are normally gases, will come off right at the top. Those with the higher boiling points come down at the bottom. Here you will see diesel, lubricating oil, fuel oil. And right at the bottom of the fractioning column, there's a residue containing, among other things, bitumen, and we use bitumen for building. Bitumen is another name for tar. Okay. They use that in a road building. So in the petrochemical industry, all the fractions are used. Now, we'll come back to this fractional distillation of crude oil specifically when we do organic chemistry. Okay. And that would be a little bit later on in the syllabus. All right. Now, I just want to go back one. Fractional distillation. Okay, applications of distillation. Why do we use distillation in a laboratory? So that we can have, for assurance, so that you can test to see whether the stuff is pure or is what it has to be, because remember, pure substances have fixed boiling points, so you heat it up to that boiling point, and you can check the liquid that comes off. It should be that one done. Water purification, if you go and buy a bottle of distilled water, I don't know if some of your car batteries still are those with the little caps that you screw open, and you have to add a bit of water. You used to have to add distilled water to it. All right, now distilled water, I explained to you yesterday, they vaporize the water and condense it. All the salts and impurities will be left behind, for example, in steam irons. And where else? Desalination plants. The coast of Swakopmund, there's a desalination plant. They remove the salt from the seawater so that it can be used for good for human consumption. No. Okay. Alcoholic beverages. They do distillation. If you go and stand in front of a shelf, you can buy things called beer, malt, and wines. Then, in a different category, goes the so-called spirits, whiskey, brandy, whatever. Okay? The spirits, they started out by fermenting the grapes or the malt and hops or whatever carbohydrate source they start off with. Then at a certain level, when there's a certain amount of alcohol in it, hereby 11, 12, 13%, the alcohol kills off the enzyme that does the fermentation. So what they go and do is to increase the alcoholic content, because if you go and look on a bottle of brandy, you'll see the alcoholic content is like 40% or 50% alcohol, while beer and wine vary from 3% to 11 or 12%. So by distilling the alcohol off from the fermented carbohydrate source, we can make whiskey and brandy and rum and any of the so-called spirits. They are usually also more expensive than just a bottle of wine. Okay. Perfume industry. They extract oils from plants and flowers. They don't do a normal distillation of the parts, but they extract it with a so-called steam distillation. They pass steam through it at fairly high temperatures, and then the oils dissolve in the steam, and from that then they can extract the oils, because the plant matter, etc., tends to want to burn at higher temperatures. And similarly, food flavorings, for example, citrus oil is also extracted by a steam distillation. You don't need to worry too much about that. All right, now, we have now had a look at filtration. We have had a look at distillation. And crystallization. So, filtration, crystallization, distillation. Now, the next way of extracting substances or separating mixtures from each other is something known as chromatography. All right? Big words. Lots of new words to go and learn. Chromatography. Now, chromatography separates different substances in a mixture because different substances have different solubilities. So what you're going to do is, this mixture is allowed to dissolve, for example, if it's water soluble, it dissolves in water. And then you draw the water up, for example, a column of sand or a paper. Okay? And then we find that the least soluble substance gets left behind sooner, and the more soluble substance will move with the water or the solvent up through the paper. I have a picture of it over there. And it's much too... Now, here I have a picture of a chromatography process. You start off, you have either a container. Here we've got a rod onto which we've clamped a piece of paper. It's just a normal piece of filter paper, works very well. And then over here, on the filter paper, they've drawn a pencil line there. Okay? Why do we work with pencil? Pencil is not water soluble. Okay? Because we're doing a water chromatography. Then, on the piece of paper, they've marked a spot with a red Kokie, or green ink, and blue ink, and black ink. And they leave it. The end of the paper is touching, or just slightly a millimeter or two into the water. And what is going to happen over here, we can see, can you see over there? The water has been drawn up through the paper. All right? And can you see the spots have moved? It no longer lies there. Why? Because the ink is water soluble. And it draws it up the chromatogram. A little while later, this is what we get. The spots have moved. We can see that the red ink that we started with is starting very slowly to separate there. You can see some yellow and there's some orange. Okay? The green ink we started out with very clearly contains yellow and blue. The blue ink contains blue and purple. And the black ink contains some yellow, there's some orange, there's some purple if you look carefully, if you're allowed to move further, and there is some blue. Do you follow me? So we can allow these substances to be pulled up through the chromatogram, and then when the water level reaches the top of the paper, you remove it from the water, because if you left it in there, the water is going to keep moving up, and it's going to move all the spots right to the top of the paper. All right? So eventually, you will get a piece of paper on which there are different color markings. And from that you can recognize, oh, my blue ink or my black ink contains blue. If you look at this chromatogram, the fact that this blue does not go up to the level of that blue, you can say it's not the same color blue. All right? Because the same pigment will have the same solubility and it will be carried up to the same level. You're all following me? All right. So we separate things because they have different solubilities. Now this is very simple. We can do this in class one day. We can try and do it this afternoon. If you've got some water-soluble Kokies, not permanent ones, we can give them a go. I think they are water-soluble. All right. We can do a couple of chromatograms. Okay. We'll use filter paper. This is probably filter paper. Okay. You get specialized chromatogram cards that's like a metal sheet, and on it is like a silicone powder that's like half dry on it. You can scratch it off with your finger. And then the solvent is sucked up or is drawn up through that silicone gel layer. You can do chromatograms with columns of sand. Where the solvent will be drawn up the column of sand, or sometimes you can allow it to move down. The more soluble one moves the furthest, the least soluble one does not go as far. All right. Yeah, on the next picture, I've just done, it's actually upside down. The red pigment, can you see clearly, is breaking up into pink over here, and there's a bit of red over there. And what else? Some blue. Over here they've done one with a brown ink pen. Now we can do similar ones this afternoon. There's one with brown ink. Well, it seems as if there's some black over there. We have some pink over here and some yellows, but I think over here it separates into yellow. So the orange is probably the pink and the yellow separating from each other. The black ink on this chromatogram very definitely got some blue ink in it. There's some red ink in it. And there's definitely some yellow ink in it. If you had to hazard a guess, would you say that that yellow and that yellow is the same pigment? Probably it's more or less been carried to the same level. Okay, I just don't know if they've been in the water the same amount of time, so it's difficult to say that. The green ink consists very clearly of blue and yellow. The blue ink, well, I think there are 2 or more dyes of blue, or maybe even there's some blue in it, and there's maybe a little bit of purple in it. And the purple ink is just one color. All right, so that's made up from one type of dye. Black ink is probably 3 different colors of dye added. All right, to make brown ink, there's a bit of black ink, there's a bit of yellow ink in it, maybe even a little bit of red or pink. Okay. Red ink contains blue, it contains red, it contains pink. And that is why different pens, if there are different makes, they've got slightly different compositions to their ink. So one pen will write a dark blue, and another one will maybe write a lighter blue. Now, forensic science can use chromatography when they say the note was written with this ink pen. Then they can identify what dyes were in the ink, and they can contact the companies and figure out what, or if they've got a pen and they want to test, is it possibly this pen that wrote it? They take a sample of the pen and they take a sample of the note, and if it separates into the same ink dyes, there's a very good probability that it was that pen. Do you follow? Okay, that's chromatography. So chromatography then is used, seriously, honestly, did I throw it away? Undo. Okay, there it is. So chromatography works like that. Now, chromatography has got some other uses. It's not just playing around with different pigments of ink. If I want to test a sample of urine, for example, and I want to test, there shouldn't be lots of sugars and proteins in your urine. So I can go and take a sample of urine and I can do a chromatogram, and the different salts that are dissolved in the urine will separate out on a chromatogram sheet. But these substances don't have color. So I will take a certain size chromatogram. In the laboratories, they will know what sizes work, and they will leave it to draw up the urine for a specific amount of time, because they know at that point the solvent level is at the top of the chromatogram. They will remove it, but there won't be any spots on it. Then what they will go and do is they will treat the chromatogram with something known as a locating agent. Now, it's a chemical substance that they will spray over it or dip it into, and what will happen is this chemical substance will react with the sugars or the proteins, and it will make a visible spot so that you can see it. All right. Now, for different things, we have very specific locating agents you don't need to know. Okay, you don't need to know what the name of the locating agent is. Just know if you have a chromatogram that is colorless, you can't see the spots. How can you identify the spots? By treating it with a locating agent. Then, a mathematical value can be calculated from a chromatogram. We refer to it as an RF value. And it's very simply the distance traveled by the spot over the distance traveled by the solvent. Let's go back to our chromatograms. Let's say we want to get the RF value for this pink color. Then, because they sort of spread and they elongate, we will work more or less from the center of the spot, so that we can do it consequently with all the spots. So how would I figure out the RF value? Now, all of the spots probably started over here on a line. The pink color has traveled that distance. The solvent should be more or less over there. So how do we work out the RF value for the pink pigment in this red dye? We will measure the distance from where it started, okay, over the distance that the solvent moved. And that will give you an RF value. It will always be less than 1, because if it moves up to the solvent, it's the same amount divided by the same amount. It's going to give me 1. No. Okay, so we find that the most soluble substances will have a value very close to 1. The least soluble substances will have a value far away from 1, 0.25, for example. Eh?
Love to hear from you. Send us your views, comments, and videos with your name and town to the One Africa TV's WhatsApp on 081 200 6659 or send an SMS to 555. One Africa TV. It just gets better.
I just love it when Otherwise put some Spanish in there. But first you gotta smoothen us out a bit. You gotta hook us up with something in Spanish, my friend.
What do you want me to say?
Just say, you know, abratricido, whatever. Just say.
Gracias por tenerme aquí. Me alegro de estar con usted.
Okay. Yeah, and then when I say, I'm serious about it, because we as Namibians never had the experience of getting some international languages in our music, and you bring that element. I think that's what makes you different and also stand out at the same time.
Modesty apart, like this is probably the first time that I get nominated, and I feel very confident about a certain outline.
Come to ShopRite's birthday for more low prices. Like 2 liters Nam Milk Omaere, only $34.99. And 2 liters Crystal Gold Sunflower Oil, just $44.99. Go Wololo with our more low price birthday.
Share with us on #LearnOn1. Tell us what you're learning and where you're learning it from. Send us your name and town to the One Africa TV's WhatsApp on 081 200 6659 or send an SMS to 555. One Africa TV. It just gets better.
I used to love this bracelets,
shiny things.
You know, shiny blank, yeah. You know, and then the Herreros, they would say, blangue.
Hola, more video. Yeah? You said you were close to that one because they are both Kwaito guys.
Yeah, very close. You know what happened? This other auntie of mine brought me a keyboard from America, a keyboard. So I used to play Twinkle, Twinkle, Little, just there every day to master that thing.
Onjero donganado banuka titingu numukade nduka tuya pewa. Onjero donganado banuka titingu numukade nduka tuya pewa.
accommodation is the ability of the eye to focus on distant and near object, and I bring it in contact with the electroscope. What you must keep in mind is positive charge can't move. It is the negative charge that moves.
So the first one, EF, is then going to be 0 minus negative 2 over 4 minus negative 4. Look at my signs. If you go wrong there, if you don't substitute in brackets, you're definitely going to get wrong answers.
To carry on with the work. In the previous period, we had a look at measuring time, the apparatus, very quickly. What did we say do we use to measure time with? A stopwatch, all right? And it can be a digital one, or it can be an analog one, a digital one, and an analog one. It doesn't matter, but remember we said that when we measure hand time, our limit of accuracy is 1/10 of a second, even though a stopwatch can give 100th of a second. No. All right. That's just due to human error. Then temperature, we said we use a thermometer. What is the SI unit for temperature? Kelvin. Okay, and I explained to you at 0 Kelvin, particles have no energy. All right. And from there, there's a direct proportionality in the terms of the temperature in Kelvin and the amount of kinetic energy the particles contain. The next quantity was mass. Mass is the amount of matter, and it's measured in kilogram. The apparatus we use is a balance. All right. Then we said volume can be measured using a measuring cylinder or a burette and a pipette. I don't want to say much more about that. Just remember when we work with a burette and a pipette, if you run the liquid out, you don't blow out the last drop. There's always a little drop stuck in the bottom of the apparatus, but it's been calibrated with that drop left in it. No. Unit for volume, cubic, centimeters, meters, or millimeters. And then we had a look at purity of substances. Pure and impure. If something is pure, it means it consists of one kind of substance. It has a fixed melting and boiling point. If you want to separate the substances, if it's a compound, you need to break chemical bonds. All right. They occur in a fixed ratio in a compound. If we have an impure substance, it's usually mixtures. When we have a mixture, it's two or more substances put together, no chemical bonds. We find that mixtures melt and boil over a range of temperatures. Okay, so that is where we stopped in the last period. Now today, I want to carry on. We are still busy with pure and impure substances. One of the properties then, if something is pure, is that it will melt and boil at a fixed temperature. That's melting point, and the upper one is always the boiling point. All right. Why is purity important? If I want to bake a cake, the recipe says 2 cups of flour and 1 cup of sugar, but if I messed some salt in my sugar, and I took a cup of the sugar-salt mixture, will my cake taste the right way? No. Now, it won't be very poisonous, but let's say I am making medicine. And the medicine has got a specific recipe with specific chemicals in it. then I will find that if I don't work with pure substances to make my medicine, I can end up making something that is quite poisonous. All right. So we need to know when we are working with something that is pure. And to check to see whether something is pure, we have to go and have a look at fixed melting points and boiling points. If I look at this graph, what substance do you think we check the melting and boiling point of on this graph? Yes, why do you say that? Yes, remember, water melts at 0 degrees Celsius and it boils at 100 degrees Celsius. Okay? At sea level, I'll explain something to you in a moment. Yes, if it is pure. Okay, now, before we go on, I want to, in terms of when a liquid boils, when I said water boils at 100 degrees Celsius, there was a query, does it always boil at 100 degrees Celsius? Does water always boil at 100 degrees Celsius? No, it doesn't. In fact, people climbing Mount Everest have quite a big problem with water boiling because there it boils at like about 60 degrees, so it's not hot enough to cook their food. Okay? How does it work? At what point does a liquid boil? What factor influences the boiling point? Air pressure, or the pressure on the surface of the liquid. If it's an open container down here on Earth, it's air pressure. We know if you go to Swakopmund, at the coast, the air pressure is slightly more than inland. The pressure is very slightly less. You also know if you go to the sea and you make yourself a cup of coffee, you burn your mouth. Why? Even if you make it with the exact same proportions, the water boils at a slightly higher temperature. So when does a liquid boil? It's fairly simple. If I have a container, okay, and I heat it up, I've got some, let's say, water in this container. When I start heating it, if you could look in the container, go home this afternoon and put some water in a pot, okay? And initially, you find tiny little bubbles appear on the surface, on the bottom. What is in that bubble? Where does the air come from? Water vapor. Yes. In that little bubble, what happens is the heat from the heating source heats up the water at the bottom first. So some of those particles gain enough energy, they can overcome the attractive forces and they make a little bubble of water vapor inside the water. Or whichever liquid it is, it would be the vapor of that liquid. So, say weer? Yes, because some of it will escape eventually. Now, this little bubble starts rising up and then it disappears. Why does it disappear? As it goes up, the water is cold, so the vapor inside that little bubble condenses and it forms a liquid again. But eventually, as this water now starts heating up, okay, and we get more or less the same temperature throughout, at a certain point, the water inside this container has enough energy to cause a little bubble of which the vapor pressure inside the bubble is equal to air pressure or the pressure on the surface of the liquid. And at that point, a liquid will boil. So, if I have a pressure cooker or in a car's radiator, the pressure on the surface can become much bigger before the liquid will boil because it has to be hotter and hotter and hotter and hotter before there is enough pressure inside the bubble for it to burst open on the surface. Do you understand? So that is why pressure influences boiling point. In general, the higher up we go, the less the pressure, so what's going to happen to boiling point? It's going to become lower because the little particles of vapor in that bubble needs less energy to get the same pressure to be able to burst open on the surface. So technically speaking, a liquid will boil, not specifically at a temperature, but a liquid will boil when the vapor pressure inside the liquid is equal to the pressure on the surface of the liquid. Does it make sense? Okay. So just very simply in terms of the boiling point of water, technically speaking, when I'm in class and we're busy with science, when I talk about the boiling point of water, I actually mean the boiling point of water at sea level. Okay? Yes. Here, it's going to boil much faster. No, it's going to take much longer to boil. Yes. It'll be able to get hotter and hotter. Yes, yes, yes. That's what they do when they distill water in a factory. They don't boil it up to 100 degrees Celsius because it's too expensive. So to distill water, they do it at negative pressure. Then it boils easier. Do you understand? Yes, yes, yes. Okay. All right. So that is with the boiling point of a liquid. Okay. Now, we say if something is pure, it has a fixed melting and a fixed boiling point. All right. When I have, let's take for example water, and I go and add some sugar into that water, and I go and test to see what the boiling point would give me now, I will find that more or less here, above and beyond its boiling point, it's usually going to go slightly above it, not lower. We find in general that impurities, now let's make our impurities, make them blue. Okay, impurities lowers the melting point, but higher the boiling point. So what do impurities do? It pushes the melting point and the boiling point further apart. All right. So that is why the boiling point on this graph, it's impure water, is above 100 degrees. And does it give me a steady amount above 100 degrees? No, you can see it's not fixed at one specific amount. So we say, if a substance is impure, the easiest way to check purity is if it's got a reasonable melting or boiling point, is to test the melting and boiling point. Okay? If something is impure, it melts and boils over a range of temperatures. All right. In the European countries where it becomes very cold in the winter and the water on the roads freeze and it makes ice, what do they throw out onto the road? Salt. What does the salt do? It dissolves in the water and it pushes the freezing point down so it doesn't freeze at 0 or minus 1 or 2 degrees Celsius. What do we do in a car's radiator? We add antifreeze. Why do we add antifreeze? Because in the winter, when the temperature drops radically, it goes below 0 degrees, what's the water going to do in the radiator? It's going to freeze. What does the antifreeze do? It prevents it from freezing because it lowers the freezing point, maybe let's say down to minus 20 degrees. So here by minus 1, 2, 3, 4, 5, 6, 7 degrees, it does not freeze. Okay, the antifreeze that we add is an impurity to the water. It pushes the melting point down and the boiling point. This is in your textbooks. They're on page 60 and 61. There they have the graphs with the melting and the boiling point. No? Okay. And, all right, now, the next thing that we have to have a look at is, if something is impure and I want to try and purify it, how do I do it? There are various methods, but it sort of depends on what you've been given. If, for example, I have a mixture containing water and sand, one way of doing it is to filter off the sand. Okay. But the sand is insoluble, so it will be left behind in the filter funnel, and the water that is soluble will run through. Would I be able to separate a mixture of, let's say, Oros and water with filtration? No. Why not? The Oros is soluble in the water. So when will we use filtration? When the insoluble substance is mixed with a liquid. Do you understand? Yeah. If I had a bit of petrol, 2 cups of petrol, in the one I add a spoon of sugar, and in the other I add a spoon of salt, and I shook it up. The sugar is going to dissolve. Can I get the sugar out from the petrol by filtering it? No. Can I get the salt out from the petrol? Yes. Why? Because the salt is insoluble. Huh. So when do we use filtration? Is if we have a solid substance that does not dissolve in a liquid. Whatever the solvent is. Now there are specific terms when we want to filter. The apparatus is a funnel, a glass funnel. You could also call it a filter funnel. Sometimes they're made from plastic. It doesn't really matter. Okay? Then we have a filter paper that is put into the filter funnel. You fold it up into the shape of a cone. Okay, and it fits into the funnel. And then you go and pour everything, your whole mixture, through the filter containing the filter paper. We find that the solid part, the sand for example, is going to be left behind in the filter. Okay? The sand is left behind in the filter. We call the sand, the stuff that is left behind is called the residue. You must know the term, no? And then the stuff that runs through is known as the filtrate. In this case, if it was sand and water, sand is the residue, water is the filtrate. Another way of separating substances is by a process known as crystallization and recrystallization. Now, have you ever seen, if you go to Walvis Bay and Swakopmund, especially there in Walvis Bay, there are certain areas in Swakopmund that as you drive along the coast out of Swakopmund, you find there are pools of water, okay? And sometimes they've got different colors. Some of them are like slightly pink and the others just look like the color of water. They are busy with a process known as crystallization. Now, how does crystallization work? If I take, let's say I've got water and normal table salt, okay? I take the water and I add table salt to it. I stir it, the table salt will dissolve. I add some more table salt. I stir it, it's going to dissolve. I warm up the water, I add some more table salt. It's going to dissolve. Okay, now, once all the table salt is dissolved in the water, I say to you, okay, now I want you to extract the salt from the water. What are you going to do? We are going to evaporate the water. Will the salt evaporate? No, it's a solid. Solid substances don't just evaporate. Okay? So what we are going to do when we talk about crystallization, we are going to remove a soluble solid that is dissolved in a liquid. We are going to remove it from the liquid. For example, salt from water. And now, the basic steps. We heat the solution. This beaker containing salt and water. We heat it up. Why do we want to heat it up? Yes, we want the water over here. The water is evaporating. What is left behind in the basin? Over there, the salt will be left behind. But also, as we heat up the solution, the stuff becomes more soluble. Okay? But at a certain point, when you've evaporated usually about a third of the solution, you will have what we call a saturated. It means no more can dissolve. Okay? A saturated solution. Now you remove the heat source over here. You allow the hot solution to cool down. As the liquid cools down, the solubility of the salt in the liquid becomes less. So it starts forming crystals. Okay, so it will crystallize, you will pour off the rest of the liquid, and you will be left with pure crystals. Okay, that is crystallization. Now, recrystallization. If I take my crystals that I get from the first step, I dissolve them in water because sometimes there are impurities sticking onto their surfaces. Alright? I take them, I redissolve them in a bit of water, I start heating up the water so that I can get a saturated solution. Then I take it and I leave it to cool and it will crystallize. And if there are any impurities, they are usually dissolved in the liquid. I pour that off and you have your crystals. Something about the recrystallization in a moment. Recrystallization also means, for example, if I have a container and I've got different salts in it. Let's say I've got some sodium chloride in it, I've got some potassium chloride in it, I've got some magnesium sulfate in it. All of them dissolve, okay? But some salts are more soluble than others, okay? So if all of them are added to the solution, they all dissolve. I heat up the solution to make them all dissolve, okay? Then I allow some of the liquid to evaporate, allow it to cool down, and I will find a specific salt will form crystals at a specific temperature. Because we will find the one that is the least soluble, the one that doesn't really want to dissolve very well, will crystallize out first. And you can filter it off. Then the next one, the next least soluble one will crystallize out. And lastly, the one that is the most soluble. Now, if you've looked at the pans of water there in Walfish Bay, sometimes you will see some of them are pink. Because what they do is, they allow the sun to evaporate the water, so they don't use energy. And the first salt that crystallizes out, I don't know which one it is a specific salt. The water becomes pink because of the dissolved salts in it. Then they run that water off into a next pond, so they can remove that salt. And then they allow it to evaporate off more. And the next salt crystallizes. Verstaan julle? Okay, and so on. They can remove the different fractions. But now, that first lot that you remove won't be very pure. There's going to be contaminants from the liquid and the other salts dissolved in it. So they will be redissolved and recrystallized to get them to be fairly pure. No. Okay, so crystallization and recrystallization. Recrystallization, an impure compound is dissolved in a hot solution, or two or more substances are dissolved in a hot solution. Then they are cooled, allowing the substances to crystallize. Which one will crystallize first? The least soluble. It doesn't want to remain dissolved. The next one, the next one. Okay, so a hot solution is used because the solubility increases with an increase in temperature. As it cools down, it will crystallize, and remember, the least soluble one will always crystallize first. Okay.
I say check out this boy jive. I say check out this boy go. I say check out this boy move. If not, but not let them know. Recognize when they see and show love when they know. It's a very warm feeling when I light it up and then go. Bafana fana say bafana soul. Bafana fana say bafana cool. Bafana fana say bafana soul. Bafana, fana, say Bafana go. Let's kick it. Bafana, Bafana soul. Bafana, 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 say Bafana soul. Bafana, Bafana, say Bafana soul. Bafana, Bafana, say Bafana soul. Bafana, Bafana, say Bafana. When you feel like you go light it all up, that's when you know that enough is enough. Take it out, I'ma feel like I'ma light it all up, 'cause now I know that enough is enough. It's up. All about for we not silent, no, we scream it loud. Stay young in your heart forever. Let's stand up tall and proud and move it up where they can't see. Let's move it up, go for gold. I wanna see your hands up because it's time we let them know that Bafana, Fana is Bafana soul. Bafana, Fana makes Bafana cool. Bafana, Fana is Bafana soul. Bafana, Fana makes Bafana cool. Feel like you go light it all up. That's when you know that enough is enough. I'ma feel like I'ma light it all up, 'cause now I know that enough is enough. Let's kick it. Bafana, Bafana soul. Bafana, 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 say Bafana soul. Bafana, Bafana, say Bafana soul. Let's kick it. Bafana, Bafana, say Bafana soul. Bafana, Bafana, say Bafana soul. Let's kick it. Bafana, Bafana, say Bafana soul. Bafana, Bafana, say Bafana soul. Let's kick it. Bafana, Bafana, say Bafana soul. Bafana, Bafana, say Bafana soul. Let's kick it.
Yes. Look, Neverland, never ever, never land. Met the Christ and he turned me to a better man. When you die, tell me what's next, man. Christ is on the right, so I guess I'm on the left hand. Teach me how to dug, teach me how to dug it. Do your sin in public and then everybody does it. Do your thing for Christ and then everybody judges. But I'm in this for life, for me, hate it or love it. Chacha Kalunga, you are amazing. I look at stars and I can't stop praising. Look at the sea, no look again. Who told the water this is where you should end? Yes, greatness, greatness, Lord you are greatness. How do you know all the different faces? How do you know the amount of my hair? How do you know what I needed to hear? No one beneath, there is no one above. No one besides that compares to your love. If I slip the cliff, Lord, it's you I would call. The fame of the world means nothing at all.